For this lesson, we'll be focusing on the second portion of analog filters, which are active filters. And just like passive filters, active filters produce a frequency response characteristic based on the desired design, which passes certain frequencies and rejects or attenuates other frequencies. So what is considered to be active filters? Well, active filters contain active components such as external power supplies and op amps, and they are typically made up of resistors and capacitors. Now, the reason we use active components is because they're used as impedance converters, which means you're not going to see any inductors in your active filters. So let's jump right in with our first filter type. This is going to be our low-pass filter. Now, you're going to see some overlap between passive filters and active filters as far as the Bode plot response and maybe some of the associated equations. However, what's going to be a big difference is the circuits you're going to see. Now, the illustration below shows two different circuits. Now, this is coming from two different PE references. However, they're both the same low-pass filter. They just have different configurations. And with those configurations, have different associated equations. So keep in mind, these equations are based only off the circuits to the left. The second type of filter we have is our high-pass filter. And just like the previous slide, I provided two different circuits for the same filter. Now keep in mind, whatever circuit you have or you choose, that's going to use the associated equation with it. For this one, the only thing that's really going to change is your gain. So based on whatever configuration you have, that's going to determine which gain equation you use. As far as the cutoff frequency, both of them use the exact same cutoff frequency. Our third type of filter is our band pass filter. Now, unlike the previous two slides, the band pass filter we have here, I only provided one particular circuit, due to the majority of the PE references provided a similar circuit amongst all the books. Now, this circuit is called a multiple feedback band pass circuit. And the good news is this particular circuit uses similar equations. Now, the equations in the middle, I provided two center frequencies, as well as gain and a quality equation. And quality we'll go over later on in the later slides. But everything else about the band pass filter is very similar to passive filters. And of course, our last filter type is our band stop filter, also known as our notch filter. Now, unfortunately, a majority of the PE references didn't go into great detail regarding the band stop filter. However, they did provide a common circuit amongst all the books, as well as the center frequency equation. The good news is, a majority of the band stop filter equations and calculations are very similar to the band pass filter equations and calculations, with the exception to the center frequency as well as the gain. Since we went over a refresher for our band pass and band stop filters, now we can introduce a new variable, and that's going to be our quality factor. Our quality factor is the ratio of the center frequency to the bandwidth. In other words, when you design a band pass or band stop circuit, you want to be able to have very narrow roll-offs on your Bode plot. So that way it almost mimics a square. So the more narrow it is, the higher quality. That means your cutoff frequency is going to be exactly where you want it and your bandwidth is very narrow. So the higher the quality, the better the circuit, the better the design. The lower the quality, the worse. And you can calculate your quality by determining your center frequency divided by your bandwidth, or you can determine your quality by 1 over 2 times your dampening ratio. When working with active filters, you're going to have different response characteristics. And there's usually 3 different types. There's the Butterworth filter, the Chebyshev filter, and the Bessel filter. And depending on your dampening factor will determine what response characteristic that filter inhibits. Now, your dampening factor or dampening ratio was addressed in a little more detail and a little bit more examples in the control system second order response video. So if you want a little more practice regarding that variable, that's the video you would probably have to focus on. Now this is where I save the best for last, the switch-capacitor filter, and it has a very unique setup. Reason being is, active filters require high resistance capacitive values, and it's typically too large of an amount to fabricate on a single monolithic IC chip. Monolithic meaning one stone. And these large capacitor and resistor values make it very difficult to obtain very good tolerance values with a single IC circuit. This is where switch capacitor filters come in. Switch capacitors, you remove all the resistors and you replace it with 2 MOSFETs, a capacitor, and a 2-phase clock. And with these particular components, you can recreate any resistor value you want. In the bottom right here, we have just 2 simple equations with a single capacitor and a clock to create the resistor we want. And we'll go over this more in the example problem. All right, for our first example, I figure we jump into a good one. For this one, we want to determine the center frequency for these two cascading filters. Well, right off the bat, we need to identify what type of filters these are, and then to determine how to find the center frequency. Well, just by looking at these configurations and referring to the PowerPoint, we can already look at this and determine this first guy right here looks like a low-pass filter, because you could see that our resistor is in line with our positive input, and then our capacitor is going straight to ground. And we can say that's where our low-pass filter ends, because if you look in the diagram, you can see it mimics it almost to the T. Now we can look at our second filter. And again, looking at the PowerPoint and looking at how it's configured, you have your capacitor in line with our positive input, and then your resistor going to ground. Well, this mimics a high-pass filter. So that tells us right away that you don't have two low-pass filters, but instead you have a high-pass and a low-pass cascading together. Well, anytime you do that, you in a sense create a bandpass filter. That would make sense when you're trying to determine your center frequency. While looking at this, we can determine our cutoff frequencies for our low-pass filter, then our high-pass filter, and then once we find our cutoff frequencies, we can use this equation right down here and find our center frequency. So let's find our cutoff frequency for our low-pass filter first. So I'll do this down here, our low-pass filter, and this is going to be our cutoff. It's going to equal 1 over, and it's going to be 2 pi, and it's R1, C1. So that's going to be R1, C1. Now again, referring to the PowerPoint, this is R1, this is C1. Same over here, C1, R1. And these are going to be feedback resistors. Looking at this, we have 1 over 2 pi, and then R1 is 12K, or 12 kilo ohms, times your capacitance, which is 0.221 nanofarads. And I'll bring this all the way out here. And this is just a simple plug and chug in your calculator, which is going to give me an answer of 60,013 hertz. Or we can just round and say this is 60.0 kilohertz. And that was our cutoff frequency for our low-pass filter. I'll tell you what, I'll put that up here. Low pass cutoff equals 60 kilohertz. Now let's do my high-pass filter. So I'll do high-pass cutoff. And again, I'm going to use the same equation. 2 pi RC. Now keep in mind, I only provided the bare minimum amount of equations here for some of the problems we're doing. You might have to refer back to the PowerPoints or refer to some of your textbooks for very specific variables. So just keep that in mind. All right, moving on. So it's 1 over 2 pi, and we have R1, which is 12K, times, and for this capacitor, it's 0.265 nanofarads. And this is simple. I can just plug and chug this one in our calculator as well. And that's going to give me approximately 50,048 hertz, which we can equate to about 50 kilohertz. So I just found our high-pass filter cutoff frequency, and I'll tell you what, I'll put that up here. High-pass filter cutoff, 50 kilohertz. All right, let me clean this up so I can show you something. This was going to be plotted on a Bode plot with these two cascading filters. It's going to look something like this. Let's look at our low-pass filter. Now, low-pass filter is just the way it sounds. It passes the lower frequencies. So this was frequency, and this was your amplitude. It's going to look something like this. It's going to go straight and then roll off. And that'd be your low-pass filter. And your high-pass filter is going to pass all frequencies at a higher level and then roll off at the lower level. So it's going to look something similar to that. And please excuse the mess. I know it's not the prettiest, but it's just to give you a visual representation. So we determine with our low-pass filter that we have a cutoff frequency right here, and our high-pass filter we have a cutoff right here. And working down, our low-pass cutoff was 60 kilohertz, which means this guy is 60 kilohertz. And then our high pass filter cutoff is 50 kilohertz. So this guy right here is 50 kilohertz. So now we have our high cutoff frequency and our low cutoff frequency. So this is going to be f of h, and this is going to be f of l, because we create a bandpass filter by cascading these two together. So now we can plug and chug it in this equation over here. So we determine our center frequency by f of o equals the square root of your high cutoff, which is 60 kilohertz, times your low cutoff, which is 50 kilohertz, and then just plug and chug that in our calculator. It's going to give us a final answer of 54,772 hertz. Or we can just round and say it's approximately 54.8 kilohertz. And right there we found our center frequency for these two cascading filters. All right, so that was a pretty easy one to get our feet wet with. Let's do another example. All right, for our second example here, we want to determine the center frequency, the quality, and the bandwidth for this particular circuit right here. Well, by looking at the configuration of the circuit and referring to the PowerPoint, we can identify right away that this is a bandpass filter. And by doing that, we can determine which equations we're going to use to find our variable. The first thing I want to find is our center frequency. Well, I want to go ahead and use these equations right here. And since this is the first one on the list, I'm going to use this guy right here. So this is pretty easy. A majority of this is just plug and chug, but just get your feet wet with it. So I'm going to say our center frequency, f of o, equals 1 over 2 pi c, and it's going to be times the square root of R1. Now here's where it gets very interesting. Some of your P references may refer to R1, R3, R2 very differently. So this is where you got to refer to the PowerPoint slide. For this one, I have R3 for this resistor, I have R1 for this one, and I have R2 for the feedback resistor. For the capacitors, I have this guy as C1 and this guy as C2. So keep in mind when you refer to some of your P references and some of your textbooks, they may not actually call the same numbers as I'm calling them. That's why I have to refer to my own PowerPoint slide. So let's continue on. R1, which is 10K, 10 kilo ohms, plus, and that's R3, which is 5K, and it's going to be over. And I'm going to say R1 times R2 times R3, so that's pretty easy. So it's 10K times, and it's going to be 47K. My K's kind of look weird, don't they? And then 5K. Now here's the one thing I don't have. I don't have C. Now C, or our capacitance, is when you take the square root of C1 and C2. So let me go ahead and do that real quick. I'll keep this in the same configuration. So I'm going to say our capacitance equals square root of C1 times C2. What I have is I have my capacitance equals the square root of 0.1 microfarads times 0.1 microfarads. Well, here's the thing. Since both of these are the same and I'm squaring them, you can plug and chug it in a calculator, but you don't need to. It's going to give you the exact same capacitance. It's going to be 0.1 microfarad. So since those are the same, it just made my job 10 times easier. So all I have to do is just take this guy, put him right there. So I'll tell you what, let me plug and chug this in the calculator and bring the rest of this down. So our center frequency equals 1 over 2 pi times 0.1 microfarads times, and I'll plug and chug this in the calculator just to make it easy on us. And that's going to give me 7.989 times 10 to negative 5. And I think the rest of this I could probably just plug and chug in the calculator now that I was able to do that. So center frequency equals 127.15 hertz. And that was pretty simple. That was just a little bit of plug and chug. So I'll tell you what, I'll put my center frequency over here just as a reference, 127.15 hertz. Okay, and let me clean this up. All right, now I want to find my quality. Well, quality is determined by Q. And looking down here, I'm going to use that equation right there, which means it's going to be pi times my center frequency, which is 127.2 hertz. I'll just round. And it's going to be times C, which we just determined since these are both the same, and when you square them, it's going to give you the same answer. It's going to be 0.1 microfarads, and then times R2. Well, R2 is going to be our feedback resistor, which is 47 kiloohms. And that's just a simple plug and chug as well. So if I plug and chug that in our calculator, it's going to give me an answer of 1.878. Quality is also unitless too, hence why there's nothing at the very end of this one. There's no suffix. So if that right there, it was very simple. That's just plug and chugging and finding our quality. So 1.878. Now, the last piece of the puzzle, we're going to find our bandwidth. So we want to determine that guy. We'll look to the right. I can find bandwidth by determining my high cutoff and my low cutoff frequencies. Well, I don't have those, so I'm not going to use this guy. However, I do have my center frequency, and I do have my quality, which means my quality equals my center frequency over my bandwidth. If I want to manipulate this, I can. All I have to do is switch these two around, and it's going to give me bandwidth equals my center frequency over my quality. Well, since I have those two, obviously that's easy plug and chug. Bandwidth equals 127.2 hertz over 1.878. And simple plug and chug is going to give me a bandwidth of 67.73 hertz. Now this is a very easy example. However, let's just get our feet wet with some of these equations right here and just manipulating a little bit of it. Let's do one more example. Now, of course, I saved the best for last. For this one, we want to determine the switch capacitor filter equivalent of the following integrator circuit. Well, my integrator here is a simple resistor capacitor setup. However, for a switch capacitor filter, they remove the resistors and actually input their switch capacitor technique. And we'll show you how to do that. Well, with the switch capacitor setup, our goal is to remove the resistors. Well, the only way to do that is start using this equation right down here to determine our resistor equivalent. So in a sense, you're going to remove this resistor right here and replace it with a configuration that looks something like this. It's going to show either two MOSFETs, or it's going to show a switch with a capacitor in series going to ground. So in a sense, that's what we're going to replace our resistor with, is this configuration right here. And we can do that just by a little bit of algebra. I could see that my cutoff frequency is f of c, and it's 1 over 2 pi RC. And this was given to us in one of our textbooks. This is where the equation came from. Now I want to replace this resistor right here with this particular circuit. And the way I can do that is by using this equation right down here. So which means our cutoff frequency, f of c, equals 1 over 2 pi. Now instead of r, I'm going to put our r equivalent down here, which is going to be 1 over our clock frequency times our capacitance, and then of course times our capacitance again. Now here's where it can get confusing. This capacitor right here is this guy, and this capacitor right here is going to be our 5 microfarads. They're going to be two different capacitors, so just keep that in mind. In fact, just to keep it easy on us, we'll say this is number 2 and this is C2. C1, and we'll call that C1. That way it takes away a little bit of confusion. And of course we can clean this up a little bit. So it's going to equal your cutoff frequency equals, and by looking at this, you're going to take a little bit of algebra here and bring your frequency clock and your first capacitor up to your numerator. So it's going to look something like this. Your clock frequency times C1 over, because that was a denominator under a denominator, so it brings it to a numerator. And then it's 2 pi times your second capacitor, which is our 5 microfarad capacitor. I think we have enough variables here to start working this down. So let me move this equation up and we'll start working it down. So we have our cutoff frequency, which is 1 kilohertz, and that equals your clock frequency, which is 10 kilohertz, times C1, which we don't know yet, over 2 pi, times C2, which we do have. It's 5 microfarad. The first thing I'll do is I'll go ahead and take 2 pi times 5 microfarad, and that's going to give me 10 kilohertz times C1 over 3.14, and we'll round that to 2, times 10 to the negative 5. And then we can simplify this down some more. I could say 1 kilohertz equals, and I'll go ahead and take my 10 kilohertz and divide it by my 3.142 times 10 to the negative 5. And that's going to give me, tell you what, C1 times 318268618.7. That one is definitely a lot to write down. So it looks like we have 318 million. And of course we can isolate our C1, and we're going to divide both sides by that 318 million, and that's going to give us a final answer of 3.142. This is going to be microfarad. So we were able to find our switch capacitor for this integrator circuit. So if you're going to fill this in, it's going to be something that looks just like this. And then a capacitor right there, and then that's going to ground. And this capacitor is going to be your C1, which is, we'll just say 3.14 microfarad. And that right there is going to be our switch capacitor filter equivalent. So hopefully this is enough information to get your feet wet. If you have any questions, feel free to let me know, and I hope you all have a good day.